Welcome to the course on plasma physics and applications. We have seen in the last lecture that we need to go beyond ohmic heating of a plasma to reach thermonuclear conditions. That is beyond the heating that can be provided by the electrical current that flows into the plasma. Today we will address the heating and current drive that we can obtain using waves in the plasma. We will explore what waves are available for heating and current drive, in tokamaks in particular. We will investigate the fluid dispersion relation that you have in fact derived in the first part of the course and how that can be used to decide what waves can be employed for heating the plasma. We'll investigate the resonance between waves and particles that are necessary to transfer energy from the waves to the plasma. And then we'll focus on two systems. The ion circular resonance heating system, that's based on the resonance between the wave and the ion population. We will look at the excitation, propagation, and absorption of the wave that carries the energy in this frequency range, and at practical systems that we have available today, for example in jet, and that we are developing for ITER. We will then look at the lower hybrid wave system for basically driving non-inductive current in the plasma, and explore some of the antenna features, again, for an existing system, that of jet, and for the system foreseen for ITER. I just remind you that among the different possibilities we have to heat the plasma, in addition to the electrical current that we have seen is not sufficient to reach thermonuclear temperatures, we have the injection of neutral beams that we have explored in the last lecture, and the injection of electromagnetic waves, which is again the subject of this particular lecture. That works by having a transmission line to which we couple power from an external generator, an antenna that's used to launch the waves. Of course, the waves themselves, they have to propagate into the plasma and need to be absorbed at some layer, possibly in the core of the plasma. In fact, in general, not only for the waves, but also for the neutron beams that we have seen last time, the heating effect can be combined with the driving of current non-inductively. By non-inductively, I mean driving of current that's not based on the transformer action. That's the main principle of the tokamak idea. That means that we can, in fact, lengthen the tokamak pulses, in principle all the way to steady state, and we can use this non-inductive current to locally modify the current profile and cure instabilities that can develop in the plasma. Current drive requires direct momentum injection that can be, for example, achieved using NBI. So these are just particles that go in a particular direction that transfer momentum by collisions. Or by modifying the phase space distribution of plasma particles, for example, using waves. And indeed, let's focus on using waves. Magnetized plasmas support the propagation of many modes, some of which you have already seen in this course, in the first part of the course. And these modes can be used to transfer energy, being coupled via an antenna, to the plasma core. In order to launch a wave into the plasma, the frequency and or the wavelength of the antenna wave must be chosen to satisfy the plasma dispersion relation. We also need to choose frequency and wavelength so that the energy is deposited in a layer corresponding to a plasma resonance. That's where we want to deposit the energy. That is typically in the core of the plasma, not on its surface, not on its edge. Here I'd like to remind you the main properties of the plasma dispersion relation. First, in the direction parallel to the local ambient magnetic field, which we call B0, and using the fluid model that you have developed and used in the first part of the course. Here we can represent the dispersion relation in terms of the frequency of the wave as a function of the wave number of the wave. And we notice that there are different branches, different solutions of the dispersion equation corresponding to different propagating modes. R and L refer to the polarization of the wave, the right-hand polarization corresponding to the electric field turning clockwise as the wave propagates, and the left-hand polarization L is the other way around. The electric field is turning counterclockwise as the wave propagates into the plasma. And because of this character of polarization, the R and L waves have different resonances in the fluid sense here with electron and ion populations respectively. So the R wave is the one that resonates with the electron population because its electric field rotates in phase with the motion of the electron. Of course, if we reach the frequency at which we also go on the same period as the electron gyro motion around the field lines. The same happens for the L wave, but for the ions, and of course that will be a much lower frequency. So this could be two resonant frequencies at which we could transfer energy into the plasma using waves. But we notice that this is parallel propagation, and to launch parallel propagating waves in the tokamak plasma or in fusion devices in general is actually quite complicated if the device has a toroidal geometry. So we look at the dispersion relation in direction perpendicular to the magnetic field, which is quite different. And our little sketch here of the antenna injecting energy into the plasma reminds us that, in fact, this would be the direction that we would prefer in practical terms. Again, frequency versus wave number. Here we have branches that are indicated as XM, extraordinary mode, or OM, ordinary mode, depending on the direction of the oscillating electric field with respect to the magnetic field. We also have, as we have seen in the previous picture, bands in which there is no solution of the dispersion relation. That implies that frequencies corresponding to these bands, for example in this case, don't correspond to any propagating mode in the plasma. We have two resonances corresponding to where the frequency remains finite and the wave number goes to infinity. Respectively, the lower hybrid and the upper hybrid resonances, lower and higher frequency. This would be resonances that could transfer effectively power into the plasma. In the fluid sense, a resonance corresponds to the situation in which the index of refraction goes to infinity, and so there should be absorption of the power from the wave to the plasma. However, the fluid model only gives us a general framework to consider which waves can propagate and in which geometry in the plasma, in particular in the presence of a magnetic field. But to describe how the wave energy is actually transferred to the plasma, we need to go beyond the fluid model. In principle, we need to treat the plasma kinetically so that we don't forget that there are different velocities corresponding to different ions or electrons in the two main species that we have in the plasma. In this frame, we can have a resonance between the wave and the particle. So in this case, is a resonance that corresponds to a situation in which the particle feels in its reference frame an essentially constant force because the electric field is in phase with its motion. So typically we can write that omega minus k dot v is equal to a multiple of the cyclotron frequency. Omega minus k dot v is the frequency that the particle perceives from the wave because it's the Doppler shift of frequency. V is the velocity of the particle, of course, k is the wave number of the wave. And when that Doppler shift of frequency corresponds to either 0 or other multiples of the cyclotron frequency, then we can have an acceleration of the particle that is an effective transfer of energy from the particle to the wave. We can sketch the situation in a simple way. Say take a magnetic field in the plasma that goes into the board, and there will be an electron, say, circulating around the magnetic field lines, and we can sketch a situation of resonance in which the electric field has the right frequency and the right polarization to, in fact, resonate with the electron, meaning that is essentially providing a force that's constant as seen by the electron. So there can be energization of the electron in a very effective way. The other point I'd like to underline is that in the model that goes beyond the fluid approach, in which we consider distribution of particles that are not corresponding to a single velocity for all the individuals, we can indeed have cyclotron resonances also for waves that do not propagate along magnetic field. So if I sketch the situation, say in the geometry of a tokamak, I have the resonance corresponding to the cyclotron frequency being equal to the frequency of the wave as seen by my particle, corresponding to a particular layer. Let's color this layer in a different color here. So it is important to say also that this layer is not infinitely narrow because of two reasons. First of all, because there's a distribution in the parallel velocity of the particles, and if k parallel is not zero, that will give a certain width to this wave-particle resonance. And second of all, also because the cyclotron frequency, in particular, of course, for the case of electrons, is subject to the relativistic effect, in which essentially the mass of the electron, which appears in the definition of the cyclotron frequency, is a function of velocity. So the resonance becomes velocity dependent and of finite width, which is much more effective for an energy exchange between particles and waves. So wave-particle resonance help us in transferring the wave energy into the plasma, and they also remind us that that can happen even in perpendicular or oblique propagation at the cyclotron frequencies as perceived by the moving particle in its frame of reference. Let's estimate the order of magnitude of the frequencies that we are considering here, both for the ions and for the electrons. The resonance with the ions occur at the ion cyclotron resonant frequency, which will be used for heating. And the order of magnitude of that frequency, if we speak of course of frequency, is the angular frequency divided by 2 pi, is about 15 times the value of the magnetic field in Tesla if the frequency is expressed in megahertz, and that's for a hydrogen species, for protons that is. So that means that we have if we have a field of say 3 Tesla, we have about 45 megahertz of frequency for the ion cyclotron resonance. As it is intuitive, if we now consider the case of electrons, the frequency for their electron cyclotron resonance will be much higher, and that's about 28 times B in gigahertz if B is expressed in Tesla. So for a typical tokamak device of today and of tomorrow, we have something between 100 and 180 or 200 gigahertz. Let us now concentrate on the case of ICRH, ion cyclotron resonance heating. Let's bring up again the dispersion relation, because we need to now choose which wave we use to carry the energy that we want to launch into the plasma core from our antenna. Now the cyclotron frequency for the ions is typically here, and is much lower than the lower Heisenberg frequency, which corresponds to resonance. So we are in the branch for the extraordinary mode here. That's well below the first resonance. So we are in a range that's actually reasonably well described even in the context of the MHD model, corresponding to so-called compressional Alfvén wave or fast magnetosonic wave. We refer to this wave as the fast wave for simplicity. This is the next mode. So we have to have a wave that has an electric field oscillating perpendicularly to the ambient magnetic field. So in practice, what we like to do is to say this is our tokamak cross-section, is to have, say, an antenna that's sitting towards the edge of the device, of course, that launches a wave, which is the fast wave, and that wave should reach the resonance corresponding to, for example, the ion cyclotron resonance of the ion species we want to heat. So if I represent here the ion cyclotron frequency for that species, there will be QB, which is a function of position divided by the mass of the ion. As a function of position, say R, typically the field goes as 1 over R, so I can draw that in a simple way. And the resonance corresponds at the point, let's call this resonance, where FCI, so the ion saturation frequency, is equal to the frequency I provide the plasma with. That is the antenna frequency. Let's call that F ant, the frequency of the wave I'm launching with my antenna. At the resonant layer, effects a little bit more complicated than we have the pretension of explaining here occur, but in general we expect that there will be an absorption of the power that we launch from the antenna by the plasma. Now, without going to the details of this phenomenon, which is relatively complicated, I just noticed that the fast wave cannot propagate if the density is below a certain value, so it will need to tunnel through a cutoff region at the edge of the plasma, which is thin enough for the wave to tunnel through it, but which we can't completely disregard in our model. Okay, the wave physics in a tokamak plasma is rather complex. And one of the aspects of this complexity is that tokamak plasmas contain more than one ion species. That means that the spatial relation is more complicated, but at the same time, it has the advantage of allowing different schemes for the wave propagation. For example, we can use a scheme in which we absorb the energy of the wave by a minority ion species at the first harmonic. So that means that we choose the frequency of the antenna corresponding to the cyclotron frequency, for example, hydrogen, say in a deuterium plasma, or helium-3, again, for example, in a deuterium plasma. Or we can use the second harmonic of one of the main ion species. For example, in a DT plasma, we can say we can launch a wave at 2 times the cyclotron frequency for the tritons. That's indeed one of the schemes foreseen for ether. Or we can use the so-called ion-ion hybrid resonance, which we have not calculated in the models, but which essentially is the resonant frequency that's given by the fact that you have 2 different ion species, and the value of this resonant frequency is between the cyclotron frequency of the heavier species and the cyclotron frequency of the lighter ones, and other schemes. Now, in all the schemes, the wave fields at the resonant frequency give energy to the perpendicular motion of the resonant ions, therefore creating anisotropic distribution functions and mostly trapped ion orbits. Depending on which scheme we choose for the absorption, which determines the way the energization of the resonant ions take place, then we can have a collisional energy transfer can be to either the plasma bulk ions or the plasma electrons. If we create very energetic resonant ions, then the collisional transfer will be mainly on electrons, whereas if the energetic resonant ions have a lower energy spectrum, then the collisional transfer will be primarily to the plasma bulk ions. This figure illustrates the complexity both of the wave fields that we are generating within an antenna at the ion cyclotron resonance frequency scheme, and the orbits of the energetic ions that are in fact energized by absorbing the power of the ICRH antenna. Now we can look a little bit at the details of the antenna system that we need to launch the fast wave, that is our energy carrier to the plasma core. So in a schematic way, say we come with a coaxial line. In the plasma, we connect that to a metal plate, we call it a strap. Then we have a certain current. So we close the circuit to drive this current, which of course will be an oscillating current, say at tens of megahertz of frequency. This oscillating current will give rise to an oscillating magnetic field. Let's call that B ant for B antenna. And of course, an oscillating electric field as well. So let's draw that geometry. So we say B antenna, in fact, respects the right-hand rule. Let's say the electric field of the wave that we're launching is along the direction of the oscillating current. The magnetic field of the wave we're launching is perpendicular to it, and say there is a background magnetic field, B0, in this direction. and the wave propagation vector that could be in a direction oblique to the magnetic field of the tokamak. So this is the way to respect the polarization we need to have, because we wanted to have an electric field of the wave that's perpendicular to B naught. That's an essential element for launching the fast magnetosonic wave. Now what we want to have is a transfer of the, if you like, the oscillating current energy into the wave energy. What we don't want to have is an acceleration of particles, of charged particles, in the proximity of the antenna with the large electric fields that are provided by the antenna itself. So we like to avoid that by putting a screen, which you refer to as a Faraday screen, in front of the antenna, that at least in the direction of the zero, in the direction of the magnetic field, prevents the creation of electric fields, and that is done by, say, having conductors that are aligned with the magnetic field lines. So the Faraday screen is therefore a structure that short circuits electric field, at least in the direction of the local magnetic field, which would be the dangerous direction for the acceleration of the charged particles. Of course, the acceleration of the charged particles by the electric field is possible in parallel to the magnetic field. Acceleration of fast particles, or ions in particular, we want to avoid, because that will lead to very energetic collisions of these ions onto the material surfaces around the antenna, on the antenna itself, both damaging these surfaces and producing a very strong impurity influx. So how does an antenna for ICRH look like in practice? Here is a picture of the antenna, in fact the several antennas of the jet tokamak. We have the version has been used for many years. There has two straps per antenna, producing a power surface density of a little less than 2 megawatts per square meter. And the more recent concept has been tested in the last few years, so-called ITER-like antenna, because it's a sort of a prototype for the installation on ITER. And each module has 4 straps, which allows kind of to reduce the electric field produced by the antennas locally, and a higher power density of about 8 megawatts per square meter. You can also see the bars that produce the Faraday screen in both cases. One of the issues of the antennas in the tokamak is the question of impedance matching. Of course, the impedance of the load has to be matched to that of the transmission line and the generator to optimize the power transfer. But the antenna plasma system has an impedance that can vary with the plasma conditions, in particular with the plasma conditions at the edge, including with the variations of these conditions that are associated with the very high frequency and very violent instabilities that happen at the edge. So the different concepts also need to address this issue by compensating one strap with the other, for example, and develop some sort of resilience with respect to the sudden variation of the load that edge phenomena can lead. You've seen the antenna systems in jet. Let's take a look at the whole system. Going back from the antenna, which is of course installed in the vacuum vessel, you can even see the 2 straps in an easier way here, because they are sketched without the Faraday screen. There is a vacuum feed through. There is a set of coaxial transmission lines to transmit the power with very small amounts, small levels of losses. The frequency of the ICRH system in jet is between 30 and 55 megahertz. You have the switches that allow you to test your generators on dummy loads, or of course to inject the power through the transmission line that eventually goes to the antennas. And you have the generators. We have mentioned before that ICRH works by generating energetic ions, because they are the ones that resonate with the waves. And it's interesting to see how these ions are actually measured and how we verify that they are in fact generated by the ICRH mechanism. The example shown in this slide is an experiment done at JET, in which the frequency of the ICRH system is chosen to be the third harmonic of the suction frequency of alpha particles, helium-4 ions that is. And how do we observe them? We observe them by measuring the emission profiles in a tomographic way, gamma rays that are produced by nuclear reactions between the alpha particles and beryllium impurities that are present in the plasma. And the point is that these nuclear reactions have a threshold for the energy of the alpha particles. In other words, they occur only if the energy of the alphas is larger than about 2 MeV. So if we see a signature of this reaction in the form of the emission of gamma rays, we are sure that we have energized these alpha particles using ICRH at least to levels of about 2 MeV. And this is in fact the profile of these gamma ray emissions. We can briefly take a look at the system for ICRH that's foreseen for ITER. The frequency is actually very similar to that in JET, between 40 and 55 megahertz, power up to 20 megawatts, and for a duration of 3,600 seconds. There are 8 coaxial lines, and one of the features that characterizes the ITER system, and that's one of the features that's been tested in JET using the so-called ITER-like antenna, is that the antenna has to come on a port plug. So in other words, has to be inserted as sort of a part of an arm that comes into a port, into an opening of the vessel. Here we see a picture of the antenna as it's being drawn now. You can also see how big that is. It's quite a sizable object, and you can also see that it has several straps. It's the same concept as the ones we have described before, but it has an even larger number of straps to try and reduce the strong electric fields in proximity of the antenna. It has also the Faraday screens that we have described before. To model the propagation and the absorption of ICRH waves is a non-trivial exercise. We have seen the dispersion relations in terms of course, omega versus k. That means in Fourier space, assuming that everything is of infinite size and uniform, and that's of course not the case in tokamaks. The fast wave we like to use to carry the energy to the plasma core has a relatively large vacuum wavelength. That means they cannot be properly described in a simple Fourier formalism. A full wave calculation needs to be done. And this is an example of such a calculation. On the right here you see just a still picture of the field produced by the antenna in ITER, in front of the antenna of ITER. And on the left you can see a movie that models the propagation and the evolution of the electric field in the ICRH heating of the ITER plasma. We're now ready to briefly discuss in a qualitative and somewhat personal way the pros and cons of the ICRH. As an advantage, we have an accessible and relatively cost-effective source and component technology. We are in a frequency range between, say, 20 and 120 megahertz. That's fairly easy to work with. We can have a very good coupling efficiency, and we can choose a mechanism for the absorption that preferentially heats the ions or the electrons, which can be an advantage. It gives us quite a flexibility in the operation of the system. On the other hand, among the disadvantages that I can think of, we have a fairly complex wave physics, so the absorption mechanism is not straightforward. And we have even more dramatically a problem with the strong electric fields at the antenna. These strong electric fields, especially when rectified by nonlinear phenomena such as the RF sheath, can damage surfaces, can produce impurity influx, and therefore can really reduce the lifetime of the antenna itself and of the components around it. It is also quite difficult to match the load, in particular in the presence of variations of the edge conditions such as caused by instabilities at the edge of the plasma. The antenna itself requires quite a large surface in the chamber, a surface that of course cannot be used for purposes such as breathing tritium in a blanket. And in terms of the current drive, the efficiency is relatively low, so there's not a large amount of current that's driven by a given amount of power in the ICRH. In order to drive current more efficiently, in fact, we normally think of using a different kind of wave. That's the lower ambient wave. Considered for heating and current drive, but I should say nowadays primarily only for current drive. The concept of the lower ambient interaction is based on a wave particle resonance. So this is a resonance at which, say, the n in front of the cyclotron frequency is equal to 0. So we're really going, if you like, with a wave that propagates at the same speed as a group of particles, which are therefore referred to as resonant particles. And if we take that as sort of in an optimization process for the electron population, we can evaluate the frequency at which that occurs to be about 1.3 times the square root of the temperature, if the temperature is expressed in keV, divided by the parallel wavelength of the wave expressed in centimeters. And the frequency will be expressed in terms of gigahertz. So if we take, say, 16 kV plasma and a few centimeters of parallel wavelength, we have something of the order of a few gigahertz for this wave particle resonance. That corresponds to one portion of this lower ambient branch in the dispersion relation for the fluid wave in a plasma. Again, it's the extraordinary mode that we're dealing with. Now we're already quite to the right of this plot, which means the omega over k is pretty small. We are in a regime that can be represented well by the electrostatic wave approximation. So we have a wave that's primarily electrostatic, meaning that the perturbed magnetic field associated with the wave is generally negligible. And typically for electrostatic waves, we have the need to have an antenna in the plasma. There's a minimum density that's required to launch such a wave, and so we need to be pretty much in contact with the plasma, which we have seen is not necessarily an easy condition to satisfy. What is the fundamental mechanism for driving the current using this wave? Say we have a wave particle resonance, so there is an acceleration of a class of particles, the class of particles that resonate with the waves and that has a smaller energy than the wave to begin with. On average, it will be accelerated. The class of particles that resonate with the wave but that start with an energy that's slightly larger than that over the wave, or velocity that's slightly larger than that corresponding to the wave phase velocity, on average will in fact lose energy to the wave. So the distribution function that represented here in a 1D plot in a very simple way will be modified. Again, we will push particles that are going a little slower than the wave to the right, so we accelerate them. That means that we look at the overall structure of the distribution function, we have made that asymmetric. Say these are electrons, that means on average we have changed the average velocity of the population, that means that we are driving current. And the lower hybrid interaction, because of this resonant feature, is quite efficient in doing that. That means we can have a relatively large current driven in the plasma per unit wave power. Let's see how an antenna looks like that can launch lower hybrid waves of use for current drive. To do that, we need to provide a certain directivity of the wave with a well-defined spectrum. To do that, we have decided to go in general for the idea of what we call a grill. That's an antenna made up by many in fact, phased waveguides. So the phasing of the waveguides allows the good definition of the spectrum of the wave number of the wave, and therefore to direct the propagation of the wave in one particular direction. So this is an example of a lower hybrid antenna, we call a lower hybrid grill, installed in the jet tokamak plasma. And as an example of a complete lower hybrid system, I also use that of jet. The frequency is 3.7 gigahertz, and so far the maximum power that we have delivered to the plasma is slightly above 5 megawatts. And as in the other system, we go back from the plasma from the antenna we have seen in the form of a grill. There's a set of feed-throughs here, and then there are transmission lines that pass through the concrete wall and the torus hole, and then, of course, they are connected to the generators, which are in the form of klystrons. A lower hybrid system is also foreseen for ITER with a frequency of 5 gigahertz and a power up to 20 megawatts, although it's foreseen only for the second stage of installation of heating upgrades, not for the first stage of operation. The idea is to use this primarily for driving current in a plasma non-inductively, but because of the plasma density in ITER, it will only be possible to drive current off-axis. Nevertheless, that will be of interest to control the current profile and control the regime of operation of the plasma. We are now ready to discuss very briefly and qualitatively the advantages and disadvantages of low hybrid current drive. First of all, as was the case for ICRH, there is a technology for the source and for the components that's relatively easily accessible and cost-effective. We are in a few gigahertz range of frequencies where several applications in different domains exist. However, the main advantage that we foresee for lower hybrid is the ability of driving current in a plasma in a very efficient way, at least in some ranges of the density values in the plasma. On the disadvantage line, there is also the same kind of problematic that we have for ICRH of having an antenna that needs to be in direct contact with the plasma, which can lead to damages of the antenna itself from the plasma and to the impurity production by the antenna itself or by the surrounding surfaces. It's also difficult to match the load, a load that's constituted by the antenna and the plasma together, that's therefore varying with time. And the heating efficiency is generally quite poor, as is difficult to access the core of the plasma if we go to higher and higher densities. In summary, we have seen that cyclotron resonances can be reached by fast waves for ICRH. We have seen that lower hybrid waves are primarily used for current drive, in addition, of course, to the ohmic current drive by the transformer action. We have seen that both for ICRH and lower hybrid, the direct interaction between the antenna and the edge plasma constitutes a major drawback. In the next module, we'll discuss the electron cyclotron resonance heating, its physics basics, and some of the technology aspects of it.